Second, to make that one-way trip, it requires 19 minutes. For that reason, the spacecraft actually had landed on the surface 19 minutes before we got a signal back from the planet indicating that very happy event had indeed taken place. So the happy word here at JPL, the Jet Propulsion Laboratory in Pasadena, is that Viking Lander 1 has safely landed on the surface, and pictures have been taken and are in the process of being played back. They'll be available in a few minutes, maybe a half hour, and they will be displayed on your monitors, and Dr. Tim Much, the leader of the lander imaging team, will be here to interpret them for us. Some of the things that have taken place soon after landing in connection with the science acquisition from Viking, and indeed, I should remind you that the Viking mission is a science one. The things that have happened are these, among others. The high-gain antenna has been deployed. The cover has been removed from the receiver on the biology instrument. The meteorology boom has been deployed. The pictures have been taken. Camera 1 has been stored, and camera 2 has taken the pictures, and the pictures so acquired are in the process of being played back from the orbiter.
Talk about the press center now.
The press center at Van Karman also contains a group of very elated people, and what you see on the screen is a full-scale model, a full-scale orbiter, actually. The circular structure that you see is a 5-foot diameter high-gain antenna over which the spacecraft receives signals and also sends back the scientific data acquired at Mars. You see the propulsion unit at the bottom with the bell-shaped nozzle projecting from the bottom. The white thermal blanket, the exterior surface of it, is beta cloth, a cloth made from glass fibers of the same type that race drivers use to protect themselves in the event of fire. And what you see most prominently now is the 5-foot diameter high-gain antenna. That, as I said, is used both to receive signals from the Earth for command purposes and to relay the data back from Mars. You can see 3 of the solar panels there. The third one is folded up so that the spacecraft can be put against the wall there. The solar panels are 64 square feet in area, contain about 35,000 silicon solar cells that provide about 700 watts of power to the orbiter. The other features that you can see on the orbiter are the American flag, of course, and below that you can probably discern the bicentennial symbol. To the left of the spacecraft, of the orbiter that is, you do not see the lander capsule. It does not appear in this version. This is a picture of what we refer to as the STL. That is, a TV camera is trained on this STL, or Science Test Lander. It's an exact replica of the lander that now rests on Mars. It's in the Jet Propulsion Laboratory, and its purpose is to enable us to carry out certain actions that are being conducted by the lander on Mars to see what the effects will be. For example, we can check out certain controls to make sure that they will not endanger any component of the lander before we actually command the lander on Mars to perform those operations. For example, we would want to be sure that we do not deploy the surface sampler arm in such a way as to damage it. And so we will check out things like that on the Science Test Lander before sending the commands to Mars to carry out those operations. You see the 2 front feet, so to speak, of the lander. The first picture that you'll see coming on your screens probably in a half hour or so will contain a portion of that foot pad, which we refer to as number 3, which is on the left side of your screen. The canister affair to the left of that is the cover that has been jettisoned from the surface sampler head. The two cylindrical objects that you see near the center of the lander are the two facsimile cameras that are capable of giving us color, stereo, and black and white images from the surface of Mars. The dish to the upper right is a 2.5-foot diameter S-band antenna, which is capable of sending signals back to the Earth, relaying, or rather sending, scientific data, but at a different rate from what's the case when we send the signals first by a UHF link from the lander to the orbiter and thence back to Earth. The reason that we use the orbiter as a relay, as part of a relay system, is because we get 10 times as much data back per minute as we get if we use the high-gain antenna on the lander to communicate directly with the Earth. The view now is back to the Mission Control Center at the Space Flight Operations Facility at the Jet Propulsion Laboratory. And people are getting over a little bit of the excitement and exuberance that they felt immediately after landing, but it's still a happy group of people. The man that you see on the left with rubbing his hands together in glee is Mr. Donald Harth, the director of the Langley Research Center in Hampton, Virginia, the Langley Center that managed the Viking project, and the mission, the ace, we called him, is the gentleman just lighting up the cigar in the white shirt to the left, and the man in the center of the picture is Jesse Timmons, whom I recognize from the Langley Research Center in Hampton. And all in all, it's a very, very happy group of people, and they have every right to be so. They've worked for about 7 or 8 years, a number of them, and most of them have worked very hard and have formed a very coherent, cooperative team. The Viking flight team is made up of about 750 people here at the Jet Propulsion Laboratory, of which you see only a small number of that happy group. The landing went off almost as if it had been written in a textbook. The landing time was only 7 seconds later than that predicted, and that's even in view of the uncertainties in the Martian atmosphere, since we had only remote measurements of the characteristics of the Martian atmosphere. Separation occurred at about 10 minutes to 2 this morning, and then the spacecraft was placed into the proper orientation so that when the deorbit engines were fired, deorbit would occur. That went extremely smoothly. When the points were plotted on the predicted curve, they fell almost precisely on that curve. Then came a long coast period of about 2.5 hours, during which the main operation was the acquiring of data on the upper atmosphere by 2 entry science instruments, the upper atmosphere mass spectrometer and the retarding potential analyzer. The retarding potential analyzer is the instrument that characterizes the ionic species, the ions and the electrons in the upper atmosphere, and the upper atmosphere mass spectrometer characterizes the neutral species of the atmosphere. That's a rather interesting instrument in that its whole lifetime is only about 4 minutes. It took data for about 4 minutes centered around the time of 5 o'clock this morning. We will be eagerly anticipating the results of those measurements because, as a number of you have heard, There's a question about the argon content of the Martian atmosphere. It influences a number of the things that we will be doing with the lander instruments, and so it's very important that we analyze those data acquired by the entry science instruments, such as the upper atmosphere mass spectrometer, the retarding potential analyzer, and the pressure and temperature sensors, so that we will have the best plan for conducting the investigations using the lander instruments. One of those that's most importantly affected is the gas chromatograph mass spectrometer. If the argon content of the atmosphere on Mars is extremely high, it's much more desirable to delay some of the atmospheric analyses that are planned rather than do them initially, which was the original plan. One of the reasons for doing those analyses early is to keep the instrument clean before introducing into it any possible organic material that's contained in the Martian soil. However, if the entry science measurements that we took during descent today indicate that the concentration of argon is high, we will indeed protect that instrument, the gas chromatograph mass spectrometer, and conduct the atmospheric analyses later than we originally planned. You have been watching a number of very happy people at the Jet Propulsion Laboratory, and I turn you over to Dr. Al Hibbs at JPL.
Thank you, George. You're right, happy people, including us. We're Mars taken by a camera sitting a few feet above the surface of Mars. And we're going to have with us Tim Much, his real name is Thomas, who will be telling us about it. He's in charge of the lander imaging. Tim, we're getting you all set up, and you are, I believe, in charge not only of this camera, but you now are online with your own crew. We're going to be bringing in this photograph. How many minutes we got? We've got about 3, huh? Something like that. 3 minutes away. This one will be in black and white, I presume, when it comes up, right?
That's right, yes.
Okay. So your camera will, in the subsequent times, record photographs in color.
Yes, that's right. The picture which comes down tomorrow morning will be a color picture of the Martian surface. What we'll be seeing here will be 2 black and white pictures.
I might take a look.
Yes, you can
See if we can bring up this particular picture.
Particular skyline
right.
drawing up on the screen. Is this going out now?
Now it is.
Okay. What you see here is the field of view as it would be appear to the camera number 2, which is the first camera we use on the spacecraft.
And we're going to be taking
the first picture, which will be received moments from now, is the one outlined in orange here, which is a high-resolution picture outlined by that pencil there. And the scene will come in starting at the left, and then we'll build the picture up, moving on towards the right. And it'll take approximately 20 minutes to build up that entire picture. And the object of of particular interest will be the footpad there at the right-hand side of the picture, and we'll get our first opportunity to view the interaction of the surface materials with the actual Viking spacecraft. Then there'll be about a 3-minute delay, and we'll move up to the survey picture, which is the green picture outlined in green there, and we'll start again at the left and move over to the right. This picture will take about 40 minutes to assemble, and again, the viewers will see on their screen the picture kind of marching across. At any given time, on the screen, we can display only approximately a square segment of that either picture. So it will not be possible to see the entire picture at the same time.
So we'll get about 3 or 4 squares altogether.
Well, yeah,
3 or 4 frames.
that's the very exciting news. The end of the adverse link is, which is what we'd more or less been expecting, is more or less over that stroke gauge that you can see there. If you can indicate the stroke gauge with a pencil, we're more or less expecting that the picture might cut off there. But we're now looking forward to the possibility of getting a picture all the way up to the end of transmitter turnoff, which is all the way over there, which would be just sensational, and a kind of an unexpected bonanza.
If we're level, the horizon is there. Of course, if we're on any kind of a slope, or if the horizon is hilly, the horizon may be any place, but that's a nominal sort of absolutely flat level horizon.
It's the neat thing about pictures. Everybody can do their own analysis. We're really kind of superfluous. Everybody can figure out for themselves if the scene is what they expected.
This camera that is quite different from the ones which we have used heretofore on the orbiter, which we're accustomed to a television camera that gives us one television frame at a time, but this is not that. This is one which moves up and down in facsimile style.
That's correct. It accumulates that at a fairly slow rate, and images it on a single small sensor, each picture element, as opposed to a conventional television Vidicon system where the entire scene is assembled more or less simultaneously and then read out at leisure. So this is different. It's a very nice camera. Hope I'll have an opportunity in a minute to demonstrate just what a nice camera it is.
So we're waiting for the data to start coming up.
Display coming in over here.
All right, we have something coming in. Looks like it's on.
Can you punch up for the before?
Mm-hmm.
Okay.
And there's the first piece of information coming in. That first edge on one side. Tantalizingly thin sliver of picture.
Yep, that's it. Oh, that's lovely.
Oh, more, and a few rocks.
Oh, that's beautiful. May not look like much, but it's lovely. Oh. Oh. This is.
Say something, Phil.
Yeah, I'm supposed to say something at this point. I just don't feel like talking.
Well, there are rocks.
There are rocks. Yes. There's rocks, and there's sediment, but it's just incredible to see that the Mars, is really there. There are some rather angular rocks. Looks to be a good deal of sediment between those rocks. This looks like it's hard to believe it's not another test, as a matter of fact.
It looks like something they photographed down in the atrium here.
Yes.
Well, as a geologist, at least you can say that there are rocks and they're dirt.
There's rocks and there's dirt, and one hesitates to characterize a scene almost immediately, but this just certainly doesn't have the feel of a lunar surface. It looks like a very distinctive surface. The scene is building. Yeah. I'm in correspondence here with my fellow analysts over in the imaging lander area, and they're as dumbfounded as I am. The only report I've got from these sophisticated analysts is that there's a lot of excitement over there. I've received no other particular noteworthy comments. I think that's about all you can say at this point. It's an incredibly good picture relative to what we had been conservatively anticipating.
The resolution is
fantastic.
Just superb.
The details are just incredible. The camera settings are correct. My compliments to my team members who set those camera settings some years ago. And we're just sitting here, as I guess everybody else is, just looking. We've gone through about 10 degrees of azimuth.
Actually, there'll be 3 of these TV frames that'll make the complete picture.
That's right. That's right. There's a lot more to come. And it just looks like a neat surface. It looks like a good surface to potentially to sample.
Yes, it looks like certainly can dig samples.
It looks like you could dig there to your heart's content. It just couldn't be better. There's a lot. I think many of the viewers who are familiar with some of the power photography and remember surface pictures from the moon will see intuitively that this is much different. Yes?
That's quite, you're right, it's quite different.
A lot of...
To think that the view of the horizon is yet to come.
The view of the horizon is just going to be mind-boggling. It'll be just neat. I'm sorry, was I knocking that? Yeah. Yeah, it's just been remarked to me that possibility in the lower left that there are little wind tails behind some of those boulders. That is sediment which has been possibly streamed out. Conceivably, this could be by the landing, although they're not supposed to be a great disturbance of the sediment on landing, so it's certainly possible. Indeed, may be likely that this is something in the scene before we landed. I should remark that the field of view here, haven't remarked upon that. We're looking at the surface from about minus 60 degrees elevation to minus 40 degrees elevation. What that means is that the near field, that is the bottom of the picture, is about 3/4 of a meter from the viewer, and the top of the picture is about 2 meters. Yeah. So the field of view again is from the top about 1.7 meters to the bottom about 0.75 meters. Those rocks in the rocks in the distance are about the rock there in the upper part of the screen, approximately 30 centimeters across. That is about 10, 11 inches or so. That's the large rock which is on the left of the screen. Now, what's happening is that we are subtracting lines from the left and building on the right, and your field of view then is marching across as we approach the footpad, which in a few moments will show up on the right. The sun is
apparently coming from. Well, it's coming from the right, I believe.
Yeah,
Because,
that's which is what we had hoped for.
Anticipated,
okay,
yes.
Yeah, what we'd
right.
hoped for, and that's appropriate.
Because number one was supposed to be toward the northwest,
Yes.
and you're looking almost opposite number one, so you're looking sort of to the
That's right.
southeast
we've,
or to the east.
That's right. We've landed
and
in the
it's
evening.
late in the afternoon.
That's
The
right,
sun's coming from the west.
That's right. We're landed late in the afternoon, and the sun is coming from the front right. And you can see that shadow very clearly on that rock, which is coming up on the right. That means, again, sensational. We just landed about the orientation that we anticipated.
Well, the rocks that we see in this picture don't look big enough to do us any damage. And, of course, by now we know that no rock did do us any damage.
No.
So apparently the estimate of smoothness of the surface wasn't too far off.
Yeah, I can hear you, but I'm not going to keep acknowledging. Some of these rocks obviously are angular. The one on the upper right is especially so, and this is
Looks broken.
It looks broken. This is also a feature just from a geometric point of view, which is seen here on the Earth when the wind facets boulders with sandblasting and so forth. So it's a possibility, certainly, that these particular boulders have been faceted and planed by sand-driven grains. If I appear a little tentative in all my interpretations, it's because we're going to have a lot of time to look at these pictures, and instant interpretation is always a little bit hazardous, but nonetheless, many of these boulders do look very similar to ones that we've seen in desert terrains here.
It's really almost impossible to say anything on the first view of the surface of another planet.
I can see that we're going to have a lot of fun collecting samples here. We can thread our way through these some boulders. Several dropped lines there appear as dark streaks in the picture. Subsequently, it'll probably be possible to recover those lines. But the amazing thing is, again, these pictures are so good just as they stand. We had been conservatively expecting a lot more problems. These are raw pictures in the sense that we haven't enhanced them in any way.